And our next speaker is Tomasz Melcer. Tomasz is an expert in solving problems that stretch across software engineering, machine learning, and system administration. He has 10 years of commercial experience, including implementation of classification algorithms for cancer biomarkers detection, development of software for mass spectrometry data analysis, and highly scalable systems for monitoring and predictive analysis of computer networks. A supporter of open source software, he participated 3 times in Google's Summer of Code program as a mentor for projects involving natural language processing and R libraries. Tomasz is currently working at Wrocław University of Science and Technology, where he conducts research on machine learning methods in diagnostic of eye diseases. He also works with Quantup, where he provides training and supports commercial analytical projects. When he finally gets some time free from all his projects and research, in his free time, he does even more machine learning. And when I asked him the same question that I asked our earlier speakers, on which side of the debate is he? Is AI is going to kill us or is going to save us? He said he doesn't know. He doesn't have any strong opinion about this. He thinks that it will change us. If there is a big catastrophe, like a big war, it may play an important factor, but humanity has survived worse things, and it will survive AI as well. Please help me welcome Tomasz with his talk, Software Engineer in Machine Learning World. Big applause for Tomasz Melcer.
Hello everyone, thank you for coming. I will talk today about how I perceive machine learning as a person who came to the field initially as a software engineer. That is a person who doesn't really do a lot of math, doesn't really have a lot of domain knowledge, yet and I still try to solve problems that are in different fields with machine learning. Something about me. I work at Quantup, I work at in academia, I do some big data, and if you can visit us at our meetups, be welcome. Let's start from my first real job. I was a student of computer science at I think 4th year, and I got hired to a company which worked on biomedical data. This was a small startup here in Wrocław, and my first assignment was something like this table. I got a table of numbers, and I was supposed to build cancer biomarker detectors. I was a student of computer science, not biotechnology, not medical sciences, not chemistry, so I had no idea what those numbers mean. It turned out it didn't really matter, because what I was supposed to do was to write something that builds classification models out of numbers, not out of exactly biomedical data. And actually, it wasn't like that. I got a paper, a scientific paper, please implement this algorithm. And this paper was like most scientific papers, lots of science, lots of math, but it turned out that the algorithm was pretty simple. However, to explain it, I'll start from something, a simple example. Let's say we have samples of different types of wine, and someone analyzed those samples chemically and found out that this sample has this amount of sugar, this amount of SO2, and so on, so on, so on. And some wine expert, decided from taste whether it's good or bad. And we would like to find out whether, based on this data, we can build a method to detect whether the wine will be good or bad based on those factors. So this is a simple data set, 1,500 rows, so 1,500 of samples, and just 12 features total. Not all here are visible. and the algorithm I was supposed to implement was the decision trees. This is a bit like a game of 20 questions. So we start at the top of the tree, and the model that is supposed to predict whether something is good or bad asks questions about those features we've seen in the table. So whether the alcohol content is lower or bigger than 10.2. Then, if the alcohol level is lower than 10.2, then what is the acidity? Is it big or small? And so on and so on. And after a set of those decisions, you are supposed to arrive at a conclusion. This is likely to be a good wine or bad wine. And okay, this looks simple if you have already have a decision tree built, but how do we decide what kind of decision tree is actually good for this or that case? First decision, shape. We have a lot of different shapes we can grow those trees, and if you have, for example, n cases, then the number of possible trees that decide in this data set grows exponentially. So quite a lot of decision. And it turns out the algorithm used in this paper was quite simple. Let's start at the top of the tree, decide sum split. So we decide in some way that we want to split by alcohol levels, and we have 2 branches. And when we go further in the tree, we recurse and decide again and again. We never revisit this decision. We just assume that the first decision we had is a good one. So we decide then on acidity, then we pick that node, and here we decide that no other splits make sense, so let's stop here, jump to another node, and then decide this one, this is an SO2, and so on and so on. Standard greedy strategy known from computer science algorithms. It turns out that this algorithm is not perfect. It may be that you could have built a much better tree to decide whether this will be a good model or not. However, this one is a fast one, and it turns out that in machine learning, a lot of algorithms are approximations. A lot of algorithms are heuristics that just happen to work well on the usual data we have. So, for example, you probably have heard about neural networks and how they started to gain prominence in image processing. About 6 years ago, in 2012, there was a breakthrough where a Canadian researcher decided that he doesn't want to model some specific element of this neural network called activation functions with a nice smooth curve. He just wants a single mathematical operation because it's much, much faster than to compute a nice smooth derivative of something. And it turned out that because of the way neural networks work, they just go from state to state and again and again, trying to reach some model that is actually good. And it turns out that if you make more steps, you will have better results. But more steps is more time. So we could just have shorter steps, like steps that take less time to compute, and make more of them. And it turns out that despite that this is barely an approximation of something that was somewhat theoretically viable, it worked much better than the previous solutions. Now let's focus on the questions themselves. How do we decide on what questions do we put in those trees? It turns out that the first initial idea of let's just try everything, every possible question, that is let's ask about every possible column and then every possible threshold in that column, works just good enough. It's fast enough if you have a small data set, And at the time, our datasets were pretty small. It was hundreds of rows tops, so sorting at 100 of things is a pretty fast operation. And just testing every single threshold to find out whether the split into those two subsets of data will work well is also fast enough. And I don't know if you know this name, Ken Thompson. Who knows this game? Almost nobody. He's one of the people who designed the initial Unix implementation back in the 1970s. And he said, when in doubt, use brute force. It turns out that this is a common approach in machine learning. Just try everything and figure out what's the best one. So, at some point, I had a prototype that works with different data sets that I was getting from my boss, and we wanted to test it, whether it works correctly. So we started thinking about, how do we test it? And it turns out that testing algorithms like that is not a simple thing. The simplest idea, common in computer science, in software engineering, is to have some synthetic data and then manually figure out what is supposed to be the actual result, and then code it into a unit test and run our code and figure out whether it works correctly or not. The problem is, it's not actually well known what results should we expect from even simple data sets on various machine learning algorithms. For example, I've cited here two papers, one from 1969 and the other one from 1986. The first one states that neural networks at that time cannot solve the exclusive OR problem. They are too simple for that. Almost 15 years later, someone finally figured out that it is actually possible when you do this and this and this. So if you have problems with such a simple data set, it's even more difficult to test various cases and manually figure out whether this will work or not. And actually, after I made those slides, I noticed that even decision trees will have problem with this with the data set, because, well, what kind of thresholds can we pick? For example, for column A, the only one that makes sense is something between 0 and 1. But when we split the data set into two parts, one for a's equal to 0, the other a's equal to 1, then we have a data set that has 1 0 and 1 1. And that doesn't make much sense for the greedy algorithm of decision learning. And it turns out that it will stop saying everything is possible. Nothing is well known. So another approach common to unit tests is, well, some simple data that look random or generated at random. But even if we can't do that for synthetic data, this is even more trouble for random data. So it's not really a good idea either. There's an approach that is common to some machine learning code. That is, if we have an algorithm, someone probably studied it. So we can try to reproduce the results in scientific papers that studied this algorithm, and figure out whether our implementation of the code actually works the same way as the code from those papers. The problem is figuring out how to implement those test cases is very, very time consuming. It takes a lot of time, and it doesn't really bring business value if those results are not relevant to the business, except for testing some specific cases of those algorithms. However, if you are writing libraries for machine learning, and I was at that point doing something like that is providing an implementation of the training procedure, then every of your users will try to figure out whether this is a correct implementation, whether it works just as well as what he read about those algorithms in papers. So, for example, again, if you are going to implement some, let's say, neural network algorithms, everyone, if you want to sell this code or just provide this code for free on some open source repository, everyone will firstly check whether it's good enough, whether it actually reproduces the results that are published in papers. Why? Because there's a lot of implementations that make do that wrong, that make mistakes. Another idea is to just compare implementations. Now we are at a time that most algorithms are already implemented. At the time when I was writing that code, this specific algorithm I was going to implement was not known. There were no open source implementations, so I couldn't easily check it. But at this point of time, you can pick some implementation of decision trees, tune it out. You can pick some implementation of neural networks and so on, and just figure out whether your implementation works the same way, returns the same data for the same data sets. So what I did at the time was to write a prototype in Python. Python is simple, easy code. Wrote some synthetic tests, thinking that they will work. Then I wrote some production code in C++. Coded those unit tests again, and then coded unit tests that compare two implementations to each other. And at that point, we had some idea that this algorithm is correct. This actually isn't a very complex algorithm, so it didn't take us a lot of time, but it still was a nice experience for me, who was a computer science student still at the time. So the pipeline, almost all processing that is related to machine learning has some kind of a pipeline in its implementation, and it comes from the fact that you are not just getting those numbers as is. You need to usually extract them from somewhere. And at this point, I know that every time I see a new data set, I need to ask a question: where do those numbers come from? So how do they get produced? To understand what they mean to some degree at least. And it's not things like that, which is the process that was used to collect those data. This process, well, we had a biological sample. This biological sample is ionized, so you have molecules, and those molecules, we take some electrons from those molecules so that they are ionized. Then we accelerate them in an electric field, and it turns out that bigger molecules accelerate slower than slower molecules. And the whole process is based on the fact that if it takes more time to go through that electric field, then the molecule is probably heavier because it was more difficult to accelerate. So we just put a detector at the end of the tube and measure time it took to go through that acceleration tube. And when we talked to scientists that work with this kind of process, it turned out that, well, firstly, this ionization process doesn't work perfectly. Sometimes a molecule is not just ionized with one electric charge. Sometimes it's 2 or 3 electrons fall out. So it turns out that the molecules are more charged, so they go through the tube, acceleration tube, faster. Sometimes the laser is slightly too strong, and it breaks down the molecules you wanted to see, so you actually see 2 smaller molecules or more smaller molecules instead of 1 big. And there are some other problems with this process. You usually get datasets like this one. So you see that There is probably some molecule around 2000 mass of something, some unit used in this experiment. There is probably some molecule around 230, just above 2200, right? And there are some other peaks. However, if you look at this picture, it's not zeroed. So it looks like there are molecules at every single mass, just small amounts. This is biologically implausible. So this is probably some artifact from the process of measuring. There's probably some noise and so on and so on. So you need to process this data into something that looks like that table. And here's a screenshot from some analytics software that shows several steps that are needed to reach that something like a table approach. So you have initial data, then you have slightly processed data, then you have this baseline correction on the fourth panel, which reduces this initial artifact of something, and so on and so on. This is very domain specific. You need to do that for almost all data sets in existence, and this needs to be designed for the specific data set or for the specific field. So this is not something you can just copy-paste from one project to another, usually. And in our software, this pipeline consisted of 7 steps, starting from running the biological procedure and ending with machine learning. And it turns out that each step influences the result somehow. Well, if it didn't, it wouldn't be needed, right? But every of these steps can be parameterized somehow, tuned to this or that type of biological samples, tuned to this or that type of machine performing the experiment. And for example, if you perform denoising, reducing the noise in the data, and you do it a bit less, then you get more peaks, and more peaks means that more molecules seem to be detected, but this is not always true that those molecules actually were in that sample, so you have actually a bigger false positive rate, and so on. And because we didn't really know what kind of data will our customers work with, we couldn't provide any checks on whether the parameters are correct. Because, well, one person could have worked with proteins, which are long molecules that have a lot of mass, so they focus just on the right side of the spectrum, and they can ignore this kind of artifacts here, right? So they don't bother with baseline correction. Another person could have worked with simple molecules, very small. So this is an important part of that of this process, and this is all in a single field. So some summary from that code base I worked on. About around 90% code was user interface reporting and other things that are not really related to machine learning and data analysis. About 10% of code was domain-specific computations, like exactly baseline correction, denoising, and so on and so on. Less than 1% was machine learning, and this machine learning part was actually the easy part, because it turned out that simple algorithms work quite well on this data set, and you don't really need to work a lot on that part of the process. There's the pre-processing steps, like denoising, have much bigger effect on the result of machine learning, that the machine learning was actually the simplest part from this pipeline. And now I know that this is actually true for most of the projects I have seen or heard of. Or the machine learning part is just a small bit in the whole machinery of machine learning. And well, for example, we actually spent maybe half a year coding those machine learning algorithms in that project I talked about, and the user interface took us about 2 years to get it right. so that users don't complain that something is missing or something is unclear. And yeah, most of effort is usually elsewhere. So the machine learning is that simple an element that just usually just does its job. And yeah, even despite that this is supposed to be the simple part, we still need to make sure that this model is actually useful for some things. And there are two components from the science, from the computer science point of view, of whether the model is actually good or not. First one I talked about, it's making sure that what we wrote is exactly what we thought we wrote. Like a decision tree works correctly, that the splits are computed correctly, and so on and so on. The other part is validating whether this specific approach, this specific algorithm actually works on the dataset. Because it turns out that while decision trees were working quite well on this dataset, other approaches did not. For example, at the time there were popular algorithms based on kernel methods. Kernel methods are methods that try to compute the distance between two points of data, like two samples, and figure out whether they are similar or not, and based on that figure out what would be the classification. And this approach completely did not work on this dataset, so we had to test it somehow. And when I started thinking about this, I noticed that this is actually quite similar to some other elements of software engineering we encounter. For example, user interface design. We can code any complex interface we want, but to make sure that it actually is useful, it actually does not lead to mistakes, user mistakes, we need to test it somehow externally. This is not unit tests, this is something else. The same with project requirements. We can talk to clients thinking that we understand his needs, and then it turns out that what we code, well tested internally, does not meet his expectations. So this is what validation schemes are about. And how do you validate something that turns out to be a black box? We don't actually know why machine learning models work, how and why. How, this means, well, you get a tree, right? But it's actually quite difficult to explain why this split is like this one or not. Why the top level split is the alcohol based or something else. And if you have a deep tree, for example 10 levels deep, then you are starting to lose your mind somewhere in the middle. And we don't really know also why it works. Why, for example, those decision trees work so well on this dataset and not really so well on that dataset. We have some ideas that were published in mostly in the last 10 years, but they provide only clues that may or may not be applicable to our specific use case. So we need to mostly treat those machine learning models as black boxes that just compute something, and we hope the results are good enough. Why do we still use it? Because we usually use that because we could not apply any other approach. If you could apply any other approach, this is usually a better thing to do than try to figure out how to fit in the machine learning model into the pipeline. For example, if you do optimization problems, like figuring out what's the shortest path to go from one place to another, machine learning is not a good approach. Classical optimization algorithms are much better. And we use machine learning models because they still usually work, right? The keyword here is usually. And now, the biggest problem here is that we need to quantify this word usually somehow. And what could go wrong? This is an anecdote from probably 1960s. This is a quote from Marvin Minsky, the founder of the AI lab at MIT. The the place where the most important, probably the most important place for artificial intelligence back in the 1960s, 1970s, and so on. And he had an anecdote like, this was probably from some classified project. This is an anecdote I heard of it from different sources, and every one of them was slightly different too. But this is probably the oldest version I could find. So, some military approach, some military application. Military wanted to find out whether it's possible to detect tanks on images, like satellite tanks, satellite images, and the tanks could be camouflaged, so they might not be easily visible or not. And we have a lot of images to process, satellites and so on. So we want to quickly find out whether there are some military installations and so on. So they collected some images, so they ran them through some neural network approach from the late 60s, which was a very, very basic approach from our current state of view. And it turned out that they could make the algorithm work perfectly, like 100% of correct results. And then after a few hours, engineers noticed that what actually happened was that the images were developed, well, analog with analog methods, and they were developed differently, so they resulted in slightly different shades. And the machine learning model just learned to detect whether the image was darker or lighter, and that's all. No tanks involved. And the more I work with machine learning models, the more situations like this I encounter. It turns out that it's the best way to treat machine learning models is to treat them like children who don't want to do their homework. They try to figure out what's the simplest excuse to not do their homework, or to just make it look like they are doing homework, right? And here the simplest excuse was just whether the image was darker or lighter. So what we actually want to do is to test so-called generalization. So we want to test whether the model we built actually works well on data it has not seen during the training. And there's a very simple method for that. This is called a train test split. Let's say we have some images. We just put some images away so that the training procedure, like neural networks, don't see them. We train the neural network on that on some set of pictures, and then we test it on the another one. So we pretend to the image network, no, this is all our the training set is all of our data, and we have no other data. And then at the test, at the measurement experiment, we show it things that it didn't see before. Looks simple, right? This gets complex when you don't have enough data to split into those two sets, but that's a more difficult problem. And why not just test on the same data set? Because the model could just memorize it, right? The problem of memorization. Let's say again this children analogy. Some children have good memory. They don't really want to figure out what's the mechanism behind some phenomena, so they just memorize, like a multiplication table, right? And children usually don't have a problem memorizing a simple multiplication table like 10 by 10 elements, but then applying this to a bigger problem like multiplication of multiple digit numbers becomes a problem because it's not memorizable enough. So what does it mean that some dataset was not seen during the training? And this needs to be carefully defined because it actually influences the results. So let's say we have a recommendation engine for fashion, and we have some set of Polish clothing like usual Polish clothing with winter attire, with summer attire, and so on and so on. And if we want to check if this model will work in Poland, this simple approach of dividing data into two parts is just fine. So you have data from Poland, and you split it into two parts, and test on train on one, test on another, and it goes fine. We have pretty accurate results. Will it work in Australia? How do you think? Well, we could start thinking that, well, maybe in Australia there is no winter, or at least winters are not like winters in Poland, so at least half of this model will not work correctly. But to make sure what is exactly the level of confidence we can put in this model trained on Polish clothing, we need to test it somehow, and the best way is to just find that dataset with images collected from elsewhere, like Australia, and we have explicitly to test it on this kind of dataset. So, third question, will it work in Poland? But 20 years from now, fashion changes, right? Every year there are some slight shifts in what is considered fashionable or not, and after 20 years those shifts accumulate so much that probably it doesn't work as well as initially. So we need to test it. The usual way to test those time-based shifts is to collect data from 20 years ago, train the model on data from 20 years ago, and figure out whether it works for our current data. Assuming that the shifts from the 90s to our current time will be similar in scope, in shape, in size, that will happen from now to 20 years in future. And you need to make tests like that for actually pretty much anything that is related to human behavior. Fashion is not just clothing, but, well, electronic devices may be fashionable or not, right? Some behaviors like going to cinema may be fashionable or not, and so on and so on. So pretty much everything you see that is a result of human activity, human social activity, for example, economic, needs tests like that. And again, when I started thinking about it, it turns out I knew some examples from other domains, not machine learning domains, where this is also applicable. For example, I mentioned here databases. Let's say we are building a database of customers, and being from a European country, we usually think, well, it's the simplest way to look for a customer is to just type his surname somewhere. So we prepare a database that has an index on surnames. Will it work in China? How do you think? It turns out that about 30 million people in China has the same surname. So if you have an index that has 30 million items exactly equal, it's not going to actually work very well. Moreover, when you present it in a user interface, picking a name from 30 million items is not really a good idea, right? Same with optimization algorithms. I've heard of a case where some company had an algorithm for GPS-based maps routing over the United States, and they wanted to build a product for Europe. And it turned out that European cities are built in a different way than American cities, and the heuristics that were used in this software just didn't work. The routes were longer, or in some other ways worse than competition. So they actually had to test it with real data from a different place. Okay, let's say we have some model, but we have also another model, and we need to compare them to each other. Firstly, we can have different algorithms. This is a short list of currently, let's say, popular approaches. Decision trees may be simple, like this one I showed before. Maybe random forest. Random forest is like trees, but you are doing multiple trees, probably in parallel, and you are letting them vote on the answer. Some democracy in models among trees. And it turns out that in some situations this works a lot better than just a single tree. Gradient boosting is again some voting approach, but the trees are built in a different way. Some neural networks, everyone knows them now, and there are convolutional, there are recurrent neural networks, there are hundreds of different approaches now. Some old school approaches like linear regression from 1960s or 1970s, maybe with some additional features like regularization, not going to talk about what it is. Naive bias is the most probably used, the algorithm that was the first one that actually was used by normal standard users because it was implemented as spam filters. If you have a spam filter somewhere in your main email client or anywhere else, it is likely that it works with a naive bias approach. Also, why naive? Because it puts some assumption which is not actually proper, but again it's an approximation to something that would be much harder, but it works well. This approximation in the 1960s was known more as stupid bias because they thought, who would be stupid enough to apply this algorithm? Turns out quite a lot of people now. But there's no free lunch. Every single of those algorithms works in a different way, so they can learn different things. This is called inductive bias. Inductive bias is, let's say, one algorithm, like those decision trees, make splits based on single features, so on single columns. So either the alcohol content is big or small. And it works well if those columns in this dataset are somewhat independent from each other. But it won't work well with images which, well, 2 pixels next to each other will almost usually have the same color, right? Usually the pixels next to each other don't differ that much. And this turns out to be a problem for decision trees. Also, some other usual things like whether it's slower or faster. If you have a big data set, you need to be careful about speed of the algorithm. If you have a big data set, you might need some more memory or control the data set size. And algorithms also have some machine learning properties that are different between each other. Like stability, again, if you have a decision tree, then those decisions are sharp. So if you slightly move above this level of alcohol of 10.2, then it turns out that you are ending up in a completely different part of the tree, and the decisions might be completely different. This property is called lack of stability, and stability is actually a pretty useful feature in general. So in most applications, you are not going to use decision trees because they are not stable. Instead, you are using random forests, which are like decision trees, but much more stable. So let's say we have several algorithms and we want to choose between them, whether we want decision trees or neural networks or something else. And of course, as I said before, we need to test them somehow. So again, split data into train and test data sets, train the algorithm on the training set, test on the test set, and what? That would be too easy. Because it turns out that when we compare algorithms on some data set, we are overfitting to it. We are making the choice based on some random sample, which turns out that it doesn't have to be exactly representative of the whole world at this point. And again, to the analogy of children learning, if you have children that have the same capabilities, and they are solving some math test, for example, and one of them will make a mistake here, another will make a mistake in another place, and a single test won't tell you exactly what is the which of the kids is the best one, because well, the number of questions we could ask to make sure that those kids are tested fairly, in a fair way, is much larger than we could have in a simple test data set. So we are fitting to this data set instead of figuring out what is their actual capacity in terms of learning skills. So what we do is we create another data set. So when we have this original data set, we split into the 3 parts, and one part is for training, another is for comparing the models, the validation data set, and the third one is only to test the final model, the one we choose from the validation data set. And only then we can be sure that the estimate is somewhat accurate. And we could have selected different algorithms, but each of those algorithms also have some parameters. For example, when you build a decision tree, you may think that a deeper tree is better than a shallower one. You might want to control the depth of the tree, and because it might be better or worse, but this is a parameter, whether you build a tree 3 levels depth or 10 levels depth. And so to compare those 2 models, shallower and taller, you again need some validation test to compare them. And this testing of every single possible idea we may want to apply our machine learning model, this is a lot of work, and we need to somehow cope with this problem. So the standard approaches, like the ones known from software engineering, high-level libraries, because they make things simpler, easier to do, modular design, so you can swap one thing with another, and some more specific tools for machine learning. Interactive environments, they are somewhat popular in the software engineering world, at least in the parts where I used to work with, so Python programming, for example. When I started learning Java, I was missing some really good interactive environment. It was just you had to write too much code to make a simple thing to test. So expressive languages with test syntax, so that you don't have to type too much. Dedicated tools for monitoring experiments. So this is like monitoring servers, except each of your experiments is a short-lived one, and you want to firstly properly measure it, secondly store the results so that you don't need to run those experiments again and again, because the experiments take a lot of time. For example, training a single instance of a neural network for image processing usually takes hours or days. So if we want to test several types of neural networks, we actually need to be careful with time management. So it's all about tooling, and it turns out, again, I've used this tooling also for non-machine learning tasks, and they work very well for applications like testing whether some set of servers with some software work correctly or not. I had a problem to solve once, to make sure that parameters for a database, like the amount of memory set for this kind of processing or for that kind of processing, those settings are the best ones for our use case. And this is exactly the kind of set of tools you could use for this application. This is some example code for running an experiment through using an experiment manager called Sacred. You pretty much write the experiment in the run function. It's not a long piece of code. In this case, this is a simple machine learning model, but if you wanted to test, let's say, database queries, it would work just as well. And you usually have some parameters to set, so you have a specific definition of those parameters, and you just put into this framework of Sacred, and it just works. And then, I'm not sure how well it's visible. Each experiment is a single row, and each experiment has some parameters, like here, and some results here. Those are actually the validation scores from this from some set of models, and you can annotate the models, figure out whether they worked correctly or not, whether they failed at training or not, because there might be a bug in the code and the process did not actually stop correctly, and so on and so on. Those kinds of tools are very, very useful in machine learning, and if you want to experiment with anything where you need to tune some parameters, this is also a useful toolset. So some summary from me. In machine learning, a lot of approximations that make things work better, despite that they are approximations. Brute force when possible, because why bother inventing some new stuff if brute force works? The idea that changing anything changes everything in the result. And well, actually I have a little bit of time, so you probably have heard of the ImageNet dataset and how it was how it played a crucial role in the current revolution of the image processing. In the years somewhere between 2000 and 2010, most of the approaches for analyzing images were based on figuring out what features to extract from the dataset, like in my example on biometrical samples. We are trying to figure out what places have the same color, and maybe collect those areas, figure out whether there are lines, horizontal, vertical, and so on, and figure out whether you can compose these features into something that is useful for detecting cats or dogs. And they had a lot of experiments. Most of them didn't really work well, were not very usable. I think the only actual algorithm that was useful in a wide sense was figuring out how to detect faces. Those things were somewhat working even in that time. And then the neural networks came. They figured out that it does not matter. It really is not necessary to detect those features manually, that you can just put raw images into the machine learning model and it will work somehow. However, the amount of steps from the first types of models to the other type of models was so large that every single step had to be tested separately, because every single step between those two types of models may have turned out that it fails completely or it brings a huge improvement. Okay, writing ML code, building ML models, it's actually quite a lot of work, and it's research work. You don't really know that it will work correctly when you design it. Right? This is actually somewhat true to many software engineering projects, but in terms of machine learning, this is every single machine learning model has this problem. So you can't really expect that it will work well just straight away. So experiments, a lot of experiments work everything. Thank you for your attention. Are there any questions?
If you have a question, please raise your hand. I will give you the microphone.
Hi. You have mentioned some languages like R and Python. Could you tell me what libraries or other tools have you used for the production code in C++?
In C++. At the time we were working on the biomedical application, we were building everything from scratch, because firstly there were no good libraries around, and the ones that were around were open source with a GPL license, and we wanted to sell the software with something, so we couldn't just use them. Now there are some interesting libraries. Pretty much all frameworks, neural network frameworks, have a C++ layer. For example, TensorFlow has a C++ layer, which is not really that good, because it's just to provide a DSL for Python mostly, but it could be used in a reasonable way. My personal favorite is the Dynet framework, which was written from scratch to make C++ code easy to use in terms of machine learning. There are other libraries for other types of models. For example, there is this very nice library for decision trees and many derivative models from decision trees, like random forest or boosted trees, called XGBoost. And this is at this point pretty much the go-to way for me when I start working on a new data set which has a tabular data. So maybe not images, but if I have a tabular data, XGBoost is the way, usually to have a decent result in a short amount of time. And it has a reasonable C++ API too. There are some older libraries for older types of models, but I don't have actually experience with them. I know they are used in production code too, like this is libsvm for those kernel-based methods. This is liblinear, if I recall correctly, for some linear types of models and also kernel methods. And that's all I can say about C++.
Any other question? I don't see any hands. So I would like to thank Tomasz. Thank you for such a big talk. Big applause for Tomasz.
Thank you very much.